Yet. For those of you that are out there, you can see me and hear me, correct?
Yes, we can see and hear you.
Thank you. Okay, we're still missing two, but I'd like to go ahead and get started. And the first thing I'd like to do is discuss spring registration. Okay. I sent to you earlier the plan of study for the nuclear program, which is sort of the Bible for what we have to do for graduating from the program. Basically, you must take and pass each course that's listed. And by pass, it can be as low as a D-, but you must have an overall GPA of 2.0 to graduate. There are no waivers for that. Okay. If we look at the last semester, you'll be taking heat transfer course, thermal sciences lab, nuclear INC class, nuclear INC lab, nuclear simulator class, nuclear simulator lecture, nuclear topics, and then you have to do 2 socio-humanistic fine arts electives, or we give the option, instead of doing a second humanities, social science, fine arts elective, you can do a restricted elective, and that's part of what I'm going to go through with you now. If you're up to speed for the rest of your program, in other words, you've taken and passed everything else, you're only taking 16 credits this last semester. It's going to be the lightest semester out of your 4 semesters here. Students that are typically going on to a 4-year baccalaureate program will take extra credits because effectively you're not paying for them if you take 16. Actually, if you take 17 or greater, there's no more cost for tuition or anything. They will typically take general chemistry 2 with lab, and then they'll take an advanced math for whatever's offered. It could be calculus 3, multivariable calculus, linear algebra. Whatever's offered, take it. And then you're typically up around 20, 22, 23 credits, which is acceptable. Okay. If you still need to catch up on something, hopefully you could use the winter semester, which doesn't have too many offerings. There's nothing technical or math there, but you can catch up on some other associated things like your computer science elective, speech, technical writing, that type of thing. When you go to fill out the form, I have printed out a copy for both the spring and the winter semesters. I put a copy of each in the basket outside my office door, and there are a ton of registration forms there. You typically need 2 forms to fill out because of the number of classes and labs that you're taking. So all of this is already on the website, so you can sort of do this ahead of time and then just come in and fill out the forms accordingly. If you're a scholarship student, you must come back through me with the paperwork for registration, because I have to keep tabs on you to make sure you are going to graduate, and also for the costs associated with that for the program. If you're not a scholarship student, I still strongly encourage you to come back through me so that I can make sure that you're doing everything properly so that you will graduate in May. If we look at this registration form, and I'm just going to open it to the nuclear section. It's pretty straightforward for the nuclear courses, except for the labs for the simulator. The simulator is the capstone event for the degree program. Um, the course will be taught on Wednesday afternoons, 1 hour, and there's typically well, sometimes he gives a midterm, sometimes he gives a final, but there'll be a written examination as well as the homework that you do every week that will determine that grade. As far as the lab, there will be 2 hours of lab per week. There'll be 4 of you per lab session because we want you to have hands-on experience. We don't want 8 people in there where nobody's really doing anything. We narrow it down to 4. The entire grade for that course will be a 1-hour oral exam at the end of the semester, which is usually around the first week of May. And the entire grade for that is how you do on that 1-hour oral exam. If you do not pass it, then the next chance you have to redo that is spring of next year. You will not graduate this May. So I encourage you to not only spend your time wisely for your 2 hours of lab per week, but I am also in here on Mondays, Wednesdays, Thursday afternoons every week. Occasionally I'm in on Tuesdays and Fridays, and I'm here till usually 7 o'clock. You're welcome to come in and practice on the simulator accordingly. So between now and Wednesday, I'm hoping that all of you can sort of decide among yourselves how you'd like to sign up for the labs. And if I look at the simulator labs, on Thursday, we have one from 8 to 10, then another one from 10 to 12, then another one from 12:30 to 2:30, and then 2:30 to 4:30. On Monday or Wednesday, we have one that goes from 4 to 6 on each of those dates. So if you can decide among yourselves, I need 4 persons per lab. If you can decide among yourselves, that's great. I'll just let you fill it in. Otherwise, I'm going to encourage you to just put in for what you want, realizing that I will have to balance out the numbers later. So if you want a particular section, say due to your work, you have to pick somebody up, whatever it might be, go ahead and register for what you want, but send me an email as to why you need that particular time. Because again, we have to balance these out, 4 persons per lab. Hopefully you can do that on your own. I'm going to discuss this a little bit more in depth on Wednesday if you have any questions. Hopefully on Wednesday, I could put all these times up on the board and have you get back to me in class as to who wants which lab. Any questions on that? Okay. We also have if you look on Mondays and Wednesdays, we have 2 classes listed. From 2 to roughly 3, we have nuclear I and C, which is Professor Abel. And then from 3 to 4, we have nuclear topics with me. Okay? That's what's listed in the schedule, but that's not how we do things, particularly when we have a refueling outage. You're going to register for these accordingly, but the way we're really going to run things is every Monday and Wednesday, starting at 2, Professor Abel will teach Elron nuclear I and C class. And he will go to, we're going to determine the exact time, but it's going to be around 3:30. We're going to leave enough time so that at the end of this Elron class, the people that have opted for the simulator lab on Monday and Wednesday will have time to get in to start that lab. if we look at everybody's commuting time, and let's say we need to start the lab at 4:15, that's what we'll do. But that's the only way we can accommodate getting this done, plus getting everybody into the lab as scheduled. So we're going to do this for every Monday and Wednesday when the course starts. Also at that same time on Tuesdays, and particularly Tuesday morning, you're going to register for a nuclear I and C lab. And your choices are 8 to 10, or 10 to 12. Sign up for whichever. It's really not going to make any difference. What's going to happen is, as we go through the semester, and the lab is available, and the lab that we use is at Millstone Station. It's in the training building, and it's directly below the processing center where some of you went out to do all the processing for your summer internships. It's in the second building. You go through that door, and it's the first lab immediately on your right. Depending upon the availability of the lab, Professor Abel will schedule a lab for a particular Tuesday morning, and it will run from roughly 8 till 12, and he'll invite one group out there for half of you. And then another Tuesday, he will invite the other half until we get all the labs done. When you go, you'll be doing multiple labs, just like we are going to do soon at URI using their reactor. We're going to be doing multiple labs every time that we visit. Okay. That schedule of Monday and Wednesday lectures for I&C will continue until April, I will say the first week. He will have a final written exam that will wrap up that course. So by the first week of April, you will have totally completed the nuclear I&C class, and you'll have a letter grade for that course. You'll also have completed all your labs, and he will have a letter grade for that lab. He will tell you what that is, but he cannot submit that until mid-May, when the portal opens for faculty to submit grades to the registrar's office. Once everything is over there, then the rest of the time will be nuclear topics. Now, in theory, I would normally have you come in on, or have you available on Monday and Wednesday, starting at 2 o'clock to go till about 3:30 or so. Historically, what I used to do is I would invite guest speakers to come in. They would be available to speak on a topic of interest, and it could be on anything from the nuclear fuel cycle, disposal of waste, new homeland security, health physics, instrumentation, anything and everything. I would also go back to you and ask you if there are any topics of interest you would like me to find a guest speaker for. So on the remaining Mondays and Wednesdays for April into May, I would have a guest speaker in. They would talk. And the whole thing behind that was to get you familiar with other areas besides just Millstone Station or commercial nuclear power, but things that are going on in the field for either nuclear engineering or health physics. The entire grade of that course is a 20-page typed technical term paper, which is going to be due at 2 o'clock on the second Monday of May. Your entire grade is based on that term paper. Just like last year, though, we're not going to be able to do this because I can't bring the people in here and have LRON from here because they have to be vaccinated and all that. I can't bring you in here because it has to be an LRON course. So what I do is I will have lectures of interest that either the guest speakers have done or things that I'm invited to, and there are certain universities, particularly the University of Tennessee and Virginia Tech, that have a seminar once a week on some topic in nuclear engineering, specifically, or on occasion health physics. And I attend that I get a recording of that presentation, and then I send that to you so that you can review that at your leisure. Hopefully that will pique your interest so that that will be a topic that you might want to select for your term paper. So once nuclear I&C is over for nuclear topics, we are never going to meet L-RON. I'm going to send you those lectures for you to look at you're interested in. I'm going to send you a lot more than, let's say there might be 12 lectures if I went day by day for the rest of the semester. I'm going to send you more than that. And again, topics of interest to you, pick them, look at them. But again, the entire grade will be on that term paper. If you already know what you want to do for your term paper, it's not uncommon in the past to have people work on their term paper over the upcoming winter break and submit it, or even work on it over the spring break and submit it, so that you have that total course completed well before May rolls around. But that's your choice. Any questions on nuclear I&C class, nuclear I&C lab, or nuclear topics class? Okay. Final thing I wanted to do about registration is, this is on the banner on our website. It's printed out and it's in my office in the basket outside. I also keep one inside in case you want to come down and sit down and talk with me. But what I'd like to go through now is what generic areas are available to meet the requirements for the two social science, fine arts, humanistic related electives. So what I'm going to do is just go down this general area as to what satisfies that requirement. So, American Sign Language, any of those. Anthropology, any of those. Under architecture, architecture of the world would meet that requirement. Under art, any of those. Under communications and speech, journalism, film study, video study, intercultural communications, under economics, any of those topics. Under English, fiction, drama, under graphic design, digital photography, digital imaging, web design, under history, any of those. Music, any of those. Philosophy, any of those. Political science, any of those. Psychology, any of those, and there are a ton of those. Sociology, any of those. Spanish or any of the other foreign languages, any of those, or theater, okay? So basically you need two humanities, social science, fine arts electives out of the ones I just mentioned. However, if depending upon what you want to do when you graduate and you're looking to transfer to, for example, a 4-year program that might require unique electives, or you're looking to enhance your employment by having a broader background in certain areas, that's why we have that listed as restricted elective. So you can go in here and pick things that are not normally used, such as accounting, introduction to business, principles of supervision, personnel management, any of those type of things, and that would also qualify as one of those electives. And as long as you like it and I like it, it's a done deal. Um, and if you have any questions on that, let me know. If you are going on to a 4-year program at any college or university, I suggest that one of the electives you take be ethics. Because of changes in how the profession is viewed these days, both engineering and science-wise, virtually all programs at the baccalaureate level in the country now require you to take ethics. So you might as well, if you're going on to a 4-year program, take it here where it won't cost you as much or nothing and transfer it out. Okay. And again, I'm going to collect your registration forms by the end of this week. Everything I have by 4 o'clock on Friday, I will have reviewed, I will sign off on, and I will take them down to the registrar before I leave on Friday. First thing Monday morning, the registrar's office will take all of those registration forms, and they will manually register you for all the classes and labs for the spring. If there are things you want to take for the winter, also include that. They'll register you for the winter. 8 o'clock Monday morning is the first time you can register for anything for the winter, the spring. They will do that for you as a courtesy to me. I will collect all of those by noontime that they've done, that you've submitted to me, and I will put them in a yellow folder, and I'll put that in the basket or the box next to the security station, and you can pick them up at your leisure, or you can print them out yourself by going into the banner system. When you get this form back, it'll be a 1-page white type form that shows exactly what you're registered for, and then stapled to it will be the green sheet out of the registration multi-layer application form. Okay? Again, anything I have by Friday, I will turn in. Do you absolutely have to turn it in by Friday? No. But the sooner you turn it in, the sooner you can make sure you're going to get exactly what you want, particularly when you're looking at electives that you might be interested in. Some of those electives, particularly in things like photography, art, any of that, those are gone in a heartbeat. So if you're really interested in some of those, you ought to sign up for those early on. Okay. Couple of other things. Once you have registered, then you will know what your entire academic loading has been for the time that you've been here. And I want you to submit, if not at that time, shortly after that, I want you to submit a completed plan of study. Now, I sent these out to you before. I also sent one out last week. So I would like this back, and that would incorporate everything that you have. The only one that submitted that to me so far is Sarah. Hers was correct. I'm not sure I can call this up on the screen. I'm going to see if I can. For those of you, if you look at your screen, do you see her plan of study?
No.
No. Okay. Okay. Doesn't look like I'm going to be able to do that, so let me sort of walk through this with you. Okay. If you have the form, you can see me again, correct?
Yes, that is correct.
Okay. So when you have the form, in the upper right-hand corner, it'll ask your name, your banner ID number. If you're transferring in credits from any other college, or you're transferring credits in from AP credit, you're transferring credits in from CLEP, you might just put briefly like UConn, AP, CLEP, whatever, just generic up here. Then as you go down, it's broken everything down into the 4 semesters for a full-time student going through the semester, by semester for the 2 years. So if I look at semester 1, hopefully you have completed all those courses. So semester completed would be what? Fall of 2020 in each of those cases. Not asking for a grade. Let's say, for example, you had transferred in English composition from UConn. You just put in there UConn. The second item down where it says computer science elective, I would like you to write into the left exactly which course you took. Most of you took Introduction to Programming, which was CSC K108. Some of you might have taken Introduction to Software Applications, which is CSA K105. Just put that in there in that blank. If we move down to the second semester, hopefully everybody's completed all that. So everything you put in there would be what? Spring of 2021. Again, no grades are needed. If it's something you're doing later, like let's say you're taking public speaking over this coming winter semester, then you'd put to be completed, you'd put out there winter 2021. Moving down to the third semester, same thing there, to be completed would be off to the side, it would be fall of 2021 for all of those courses. Then when you go down to the fourth semester, that would be, for all of those, it would be spring of 2022. And again, for the last two electives that you see on the very bottom, on the left you see a blank. So I'd like you to put in there exactly what it is that you are listing. So for example, if you're taking cultural anthropology, you'd put ANT K105. If you're taking American Sign Language, you would put in there ASL K101. You don't have to put the title, just the number, and then off to the side you'd be completing it. If you've taken something like political science at UConn, you'd write in your political science course here, the title, the number of it, and then over here you'd put UConn. You would sign and date it at the bottom, and then I will review it as your advisor so that I'm approving everything, and I'm actually going to sign and date this thing twice before I submit it to the registrar. The only other things of note on this is back in the fall of your very first semester, most of you took General Chemistry 1. Some of you didn't take that. You took Concepts of Chemistry, which is okay. But what you need to do is mark through the line that says General Chemistry 1 and put in Concepts of Chemistry with lab, and then put in the date that you completed it. We will later have to get a course substitution form that you would fill out. I can send you that as needed. You send it to me. It's a very simple form to fill out. I will approve it. I send it to the dean. The dean of academics has historically always approved these. And what I do is I try to collect all of these at one time, because when I send in a grouping to the dean, he doesn't look at them quite as closely as he does when you send them in onesies at a time. So I'd like to collect all of these no later than November 15th. The same time you're doing this, you should be going online in our banner system and applying for graduation. Doesn't cost you anything. It's fairly simple to do. And once you've submitted that, you will get recognition or a confirmation back that you've done it. And I will get a copy of what you have applied for so that I will know that you've applied for graduation. Once that graduation application has been received by the registrar's office, when this plan of study comes to them that you have signed off on and I have approved, they will use this document as your graduation audit tool. And as long as you're satisfying this, you'll be certified to graduate. They typically do this in December or early January. And if there's any hiccups in anything, they will let you and me know that there's an issue so that you can address this by either saying, whoop, you've missed something here, you didn't apply this correctly, whatever. Or if necessary, you still have time in the spring to take a course of lab so that you graduate. But they need this and they need that graduation application. And I'd like both of those back by November 15th. Well, the application you'll just do online and I'll get verification of it. Okay. If there is anything that you're unsure about, let's say instead of technical writing, you've taken a course somewhere in writing for engineers. If that does not have the exact title, the registrar's office will not necessarily post that to your account for your official TRCC transcript because it doesn't match anything that you need. However, if you think that, that satisfies this technical writing course, then again, we could do a course substitution form, get that through me, I'll approve it, go to the dean, get him to approve it, and then it doesn't make any difference what the registrar thinks. It's done because the dean has approved it. Okay? Any questions on applying for graduation online or the plan of study? And again, what you would do in this case is, let's say you were substituting something for technical writing, you would just put in here, if you took that one course at UConn, you'd put in your UConn, and then ultimately that course substitution form, when it leaves the dean and goes down to the registrar, they will match things up. Okay. Anything I've gone over so far? Any questions on registration for the winter or the spring? Applying for graduation, completing the plan of study and getting it back to me. Any questions whatsoever on that? Okay. One other thing I want to mention today, I had an unexpected phone call about 11:45 this morning from URI. They're going to have to shift the dates that we go to see them. Long story short, apparently some of the research reactors are having fuel failures. And the NRC and DOE are looking into what these issues are. And they're trying to have a minimal disruption to classes and labs at the universities involved. And they're limiting experiments that can be done and dates that they can be done on, because I actually got to be teams from it's called NIST, that's going to come and do some preliminary experiments on the reactor to see if their fuel has this problem. So basically, for the rest of this semester, the University of Rhode Island has lost the ability to use Fridays for labs for students to take care of that problem. So I had originally set up lab dates for Tuesday, Thursday, and Friday for the week before Thanksgiving, and then again the week after Thanksgiving. So you'd only be going officially 2 times. On the first date, there's a safety overview and then a detailed tour of the lab. And then in the when that's completed, on the first trip, we were going to do 2 experiments. We've had to change those 2 experiments out because of the availability of the reactor. And then when we come back after Thanksgiving, we're going to be doing 3 experiments on the day that you come. We also have available the Tuesday before Thanksgiving, and that's an optional lab. On that lab, we typically do neutron flux. And in that case, it's an optional lab. Since there's so many of you, I'm going to try to break up whoever wants to attend, to have part of you go in the morning at like 10 o'clock to like noontime, and then the second group come in the afternoon from like 12:30 to 2:30. It's strictly an optional lab. If you come and do the lab, I will give you extra credit. If you come and do the lab and actually do a written lab report, I will give you extra credit. And I'll collect later who wants to do that. But in the meantime, for the 8 of you that are scheduled for Fridays, I'm hoping that you can adapt your schedule to go on either the Tuesday of that week or the Thursday of that week. And right now that would involve Teddy, Evan, Tony Mazzilla, Ryan McNally, Ryan Nobles, Heather, Sarah, and Ty. And I'm hoping to balance things out that I could have, of the 8 of you, 3 of you move to Thursday, and 5 of you move to Tuesday. But if you can't, we'll try to adapt whatever we need to do. Again, I just found out about this morning. Question? So I'll get back to you on Wednesday or maybe into next week to see who can move to what date. The people at URI, for a number of reasons, would prefer to keep the numbers down to where we had them. But that's the only way we're going to be able to accommodate things. We cannot move it earlier because of commitments that they have. And I can't move it to other days of the week because we're here on Monday and Wednesday for various classes. And I can't move it later in December because that would not give you sufficient time to do the experiments and then write up the experiments to get them in by the end of the semester. I apologize for that. There's nothing I can do about that. There's nothing you or I can do about that. It has to go with the failure of fuel that they're having to inspect these at all the various research reactors around the country. So I'm hoping that those 8 of you that I mentioned would be able to shift to either Tuesday or Thursday. And if we did that, that would end up with, if we use those numbers, it would end up with 13 on one day, 12 on the other. But if it ends up where we have 15 on one day and 10 on the other, then that's what we'll have to do in them. And URI will have to accommodate us. They know that. But hopefully you can shift to one of those 2 days. So for those 8 of you involved, if you could just send me an email back to let me know if you could move to one of those other dates. And then that would free up those 2 Fridays, the Friday before Thanksgiving and the Friday after Thanksgiving. Any other questions on that? Okay. One other thing I did was I sent you out last week. It's a release form that I asked you to sign and date it, return to me. I think one of you has done it thus far. The college requires that whenever there are any activities that are going on for the program that are off campus. So the fact that we're having to go to URI, and the fact in the spring that you're going to be going out to Millstone to use their INC lab, I have to have one of those forms back signed by you. Because it's basically releasing the college or me from any indemnity should anything happen to you while you're going to or from them. Normally that type of thing, if we're going to dinner meetings for professional societies like ANS or whatever, if you're in the band, then you're automatically covered. We cannot use the band for any of these because there's still the COVID protocols for spacing. So basically the only person you can get in a van is the driver, which is useless. We used to put everybody in the van, leave here about 8:45, get there by 10, spend the day, pile everybody back in and come here. So you wouldn't have to worry about driving. I wouldn't have to worry about you getting there independently. But that is not an option now because we cannot use the van. This is better than last fall. Last fall, the week before, we were getting ready to go over to start our group of experiments. And we had not concentrated them. We're going to go for 3 weeks rather than 2 weeks. The week before we were supposed to go, the governor of Rhode Island decided that she would allow no out-of-state personnel to go to the University of Rhode Island campus, either one of them, either the main one in Kingston or the Narragansett facility, period. So automatically all of our trips were canceled. We had to reschedule them for the spring and work them in. And as it turns out, because of weather and everything, we didn't go until April. So it made a very busy April because we had to do everything else we're doing, plus schedule in those labs to go to URI. So at least we're on board for that for now. And again, I'm sorry that we have to cancel the Friday sessions. But again, make sure you get those release forms back to me. And again, I need them before the first trip to URI. Any questions on anything I've gone over so far? Okay. What I'd like to do now I'd like to do any type of review you'd like to do for Wednesday's Reactor Theory exam number 2, and it's going to be on neutron interactions. And I'm thinking one of two things right now. I'm going to decide later today. I've made up the exam per se, but I'm deciding now how I want to offer it. And what I'm looking for now is on this Wednesday, I'm going to start with regular lecture. And then after that, I'm going to have the exam. And I'm looking for 2 ways to run the exam. I'm going to give you the exam, and let's say it might be as late as 1:30, and it would be due by 3:15. So I could also give you the exam. If you opted to turn it in by 3:15, I would give you extra credit. Otherwise, the exam would be due Friday at 4 p.m. So when I come in to sign off on all the registration forms and whatever, and take them down to the registrars, I would have the ability to print out all the exams that have been submitted, grade them over the weekend, and get them back to you on Monday. So this extra credit might be something in the order of 6 to 8 points. So when I give you the exam on Wednesday, which will be around 1:30, if you turn it in by 3:15, you would get whatever you get on your exam, and you'd get whatever I come up with, 6 to 8 points extra credit. And I think I already have built in on this 6 points of extra credit to start with. So you could get as many as 12 or 14 extra credit points if you did everything. If you don't turn it in by 3:15, but you turn it in by Friday at 4 o'clock, then you would just get the regular exam with those extra points graded. You would not get the extra points. So I'm tweaking the exam accordingly today. I made it up over the weekend. Again, I think it's a good one. You might not think it's a good one. I thought the last material science exam was really a good one because it brought into account both earlier work we've done for plane stress failure as well as torque, which we had just done. So I really like that one. But unfortunately, there was only a couple of you that got everything right, and particularly realized that there was axial movement of the point due to the compressive force. Any questions on the exam? Okay. Again, I'll finish that up today. I'll have it ready to give to you on Wednesday. In the meantime, is there anything you want to review on the exam, which again is going to be on neutron interactions? Anybody, any topic? Nothing? Everybody feels comfortable with that? You don't need a review. Okay? Okay, what I'd like to do now is start on chapter 9. Which is steady state reactor. And by steady state reactor, what I'm meaning is your neutron population does not change with time. Now, is that going to happen in the real world? No. It's going to be constantly changing due to fuel burnup, all kinds of reasons. But in order to understand what's going on and do preliminary calculations, we're going to assume that. Now, I could mathematically write this as either this or partial with respect to n by t is equal to 0. The partial of n with respect to t is equal to 0. What is the difference between the two? Anybody? You haven't had this in your math before? Andrew? Somebody? Yes, did you have an answer?
What is that symbol
This?
called? Yes.
That is the partial.
Huh. Okay.
That's the question I'm asking you when you see these. This does not look familiar to you. Okay. This means that n only varies with t. And it's a simple d. If I use another example, let's say I said that y is equal to 2x squared plus 3x minus 5. In this particular case, I could also write that y is a function of x. So if I took the partial of this with respect to x and did it also on this side, I would write it like this because y only varies with x. Let's say my equation was w is equal to 6x cubed sine of 4y e to the minus 6z squared. Okay? In this particular case, y is a function of x, y, and z for this equation. So there might be a reason why I want to see how my variable varies with one particular one. So in this case, if I did dw dx, I could look to see how this equation only varies with respect to x. So in this case, w varies with x, y, and z. So when we're working with chapter 9, we're saying that the neutron population only changes with time. We're not considering any other variables that can impact it. So this is the one we're working with. Okay. And to start off, what we're going to be doing is so we know steady state and we're saying our neutron population with respect to time does not change. One of the things we're going to be interested in is the multiplication factor. And what I'm going to have you do is when we start off in chapter 9, we're going to look at the multiplication factor, which is defined as K. K is and hopefully you've learned this before. K is exactly equal to 1. It is critical or self-sustaining. If it is greater than 1, it is supercritical. If it is less than 1, it is subcritical. And if you look at how things work in a reactor, is let's say you're at 50% power, and you're there steady state. Let's say you get an order that you want to raise the power to 80% power. You're going to do that by manipulating control rods. You might use boration dilution. But what are you really doing? You're changing the multiplication factor to make it supercritical so that your power would go up. Then when you go up to 80%, you will bring it back to being just critical. So in this case, if you're steady state, your K is equal to 1. When you raise the power, K has to go greater than 1. But then when you get up to where it's 80% steady state, your K has gone back to 1. And again, how do you get it to raise the power? You're going to use control rods or boration or dilution. And we're going to go over that later, and you're going to be doing a lot of this in the labs for the simulator in the spring. Okay. If we look at multiplication factor, there are different multiplication factors. And one of the ones we're going to be using a lot is K infinity, which is defined as the infinite multiplication factor. So it's K with this little infinity symbol less than that. You might also hear this defined as four-factor formula. And hopefully Professor Abel taught you this, where the four factors are epsilon, P, F, and nu, and I'm going to go through those in a minute. When we say infinite multiplication factor, what does that mean when I say infinite multiplication factor? What distinguishes this from, let's say, a regular multiplication factor or a K effective for the effective multiplication factor? What is K infinity? What does that really mean? That means we're going to determine a multiplication factor, but what does that infinity mean? How does that change things? Anybody? Nobody. Okay. Infinite multiplication factor means the reactor is infinite in size so that no neutrons can escape. We call escape leakage. So, if a reactor is infinite in size, it goes to infinity in each direction, it is impossible for neutrons to leak out, and that's how we determine what the infinite multiplication factor is. So what I'm going to do today is start to define what these four factors are, and then we're going to rework a problem that's in your textbook that's not done exactly correctly. And I would encourage you to paperclip that one page when we get there, because you're going to be constantly going back there to calculate K infinity for the balance of the semester. Any questions on what I've done so far? Okay. Question? Nope. Look. That is a four-factor formula. The one thing I like to do, and I'd like to get you to do, is mentally draw a line down between the first two and the second two. These two factors on this side deal solely with epithermal and fast neutrons. Everything on this side deals only with thermal neutrons. So whenever you write this down, you don't necessarily have to put that line and write that in, but you should mentally make sure you realize everything on this side is epithermal or fast, everything on that side is thermal. Okay, let's look at epsilon. Epsilon is defined as the fast fission factor. And what this looks at is the number of fast neutrons that cause a fast fission to create more fast neutrons. Okay? So, what material or what fuel creates fast fissions? Anybody? What creates fast fissions? Hopefully you covered that in atomic and reactor physics with Professor Abel. Correct. Uranium-238. So uranium-238 is a fast fissioning fuel. That means it will absorb a fast neutron, have a fast fission, and create additional neutrons. If we look at epsilon value, okay, in commercial nuclear power, this varies, and it goes from about 1.01 to about 1.1. For most reactors, it is somewhere around 1.03. But you design that when you do a fuel reload. For example, they're reloading out there, refueling out there now. So they will adjust the fuel mixture to get the fast fission factor to where it wants to be. And this is a positive aspect. Because we create more neutrons that hopefully survive to thermal energy. We know our neutrons, when they're fast or when they go down to epithermal, we lose them either due to absorptions or they leak out of the system. And we need at least one of them to go down and cause a thermal fission to make this thing be self-sustaining. If we look at uranium-233, uranium-235, thorium-233, plutonium-239, plutonium-241, just to mention some of them, these are thermal fissioning fuels. So in other words, a neutron has to be scattered down from fast or epithermal energies down to thermal energy to cause a thermal fission in any of those. These do not have fast fission capability. Uranium-235 only fast fissions with fast neutrons. It has no thermal capability whatsoever. If any of you remember back, the Department of Energy actually worked on creating fast fission reactors. They did this at Oak Ridge in Tennessee. And the fuel they used was only uranium-238. So we know this is the most plentiful isotope. So there's a lot of that. You don't have to enrich it. You can't really enrich it. It's just what's out there. You sort of remove the other isotopes or any impurities from it. They actually got a working fast fission reactor, but what are some of the problems? First of all, these neutrons that they're using to cause fast fission are very energetic. They're typically up in the MeV range. So whenever you have those zipping around a reactor, they can cause damage to the reactor itself, physical damage to the materials. Also, you have to have a lot of shielding to protect the crews. So they did it. They showed it was possible, but it wasn't really feasible, so it never got off the ground. But they originally did do that. Okay, to go back to this. If a reactor has a homogeneous fuel moderator mixture, fast history factor is automatically 1.0. If it is heterogeneous, E can vary between 1.01 and 1.1. You actually determine this by something called the spin-rad equation. That is really a heavy-duty equation. Spin-rad. This is sort of above and beyond where we are in this particular course. So what I will do is I will give you the epsilon value. It'll either be between this value and this value, or I'll tell you it's homogeneous and you automatically know that it's that amount. Any questions on the fast fission factor? Okay. The next term is P, and P is the resonance escape probability. And because it's a probability, P is going to vary between 0 and 1.0. Since we want this value to be as high as possible, we want P to be as high as possible. If you remember back when we were looking at the probability of an absorption or the probability of a scatter, if we look at the probability of an absorption with respect to energy, we had a curve that was decreasing, but looked like that. This is called the Doppler effect. And what happens is, if you start off with an energy if we start off with an energy that's either fast or epithermal, we need to get it down to thermal to cause a thermal fission. The only way we can reduce energy is by scatters. So if a neutron is at this energy and it has a scatter, hopefully it's going to be lowered in energy to that value. Then it has a possibility of either leaking out, being absorbed by something else, or scattering yet again to go to a different energy, and you keep this going until eventually you get down there. What we covered last week was when we looked at alpha, which how effective is scattering, or we looked at n, which is the number of scatters to get to a particular energy level, in particular thermal. You can see some of the numbers were significant. We're talking about, I think the one we worked in class was 110, and we round and change it, we rounded up to 111. So that means if you have an energetic neutron, it's going to take 111 scatters on the average to get down to thermal. What we want to do is we want to try to minimize any absorption as the thing is being scattered going down. Ideally, you would have no leakage and then have no absorption by either the fuel, the moderator, or anything else that's there. But that doesn't happen in the real world. There is this absorption due to the Doppler effect. This is also called resonances. So the resonance escape probability is the ability of your neutron population to avoid or minimize losses as it moves through this resonance region. And again, it's expressed as a probability. If you have your textbook, you might want to flip over to page 250. And 250 says that resonance escape probability is equal to E to the minus N 238, number density of 238, divided by our friend squiggle, which is the average logarithmic energy decrease, times the macroscopic cross-section for scattering. All of this times I effective, where I effective is the effective resonance integral, and it is equal to 3.9 times macroscopic cross-section for scattering divided by number density for 238. All of this raised to 0.415 power. And this effective resonance integral, what this has done is taken all these resonances and it has lumped them together into an effective integral, which says we're only going to have one resonance peak and valley. Does that happen in the real world? No. But it's a way for you to estimate what is happening with your neutron population as it scatters down from fast and epithermal to thermal values. And again, P has to be between 0 and 1. If you ever do your calculation and it's outside this range, you know it's wrong. Okay. And again, you'll start to get a better feeling for this when we work a problem. Any questions on what? Yes.
Yeah, I have a question. So the equation you have on the board is P equals E to the negative N
Raised
raised to the N 38. So, but in the textbook, it says P equals exponent. So
that is
I'm not-
exponent. That's what, so the,
The S stand for again?
out here,
No. In the effective resonance integral, there's like an
we
E.
haven't gotten there yet. That's the next thing I'm doing.
No, it's on the board right now.
Yes.
No,
F is the next,
down below
somewhere
where it says 3.9, and then in parentheses, there's like a sum with an S. What does that mean?
macroscopic cross-section for scattering. This is the same as this. Okay. If you go back, if we look at microscopic cross-section for scattering, we know what that is. If you multiply this times the number density for a material, this becomes the macroscopic cross-section for absorption for whatever that material is. This is a physical property. Remember, it's equal to rho, Avogadro's number, divided by the atomic mass. It's a physical property of whatever the isotope might be. Sigma A is the probability, in this case, of absorption. It is also a physical property of whatever that isotope is. This is microscopic cross-section for absorption, which is a probability. If you multiply this by effectively a physical property constant for the material, then you come up with macroscopic cross-section. And as I mentioned to you before, most books have this value publicized. Our book does. Some textbooks, since this is a physical constant for whatever the material is, will have this tabularized rather than that. But that's what that means.
Professor, for
Yes.
the P equation, P equals E to the negative
This one?
N, what is next
Yep.
to N?
238.
Okay.
Hopefully you're following this with me in the textbook. This is on page 250. Any other questions? Okay. If we continue on, we now taken care of epsilon and P, which are the fast or epithermal considerations. Next, we go to F, and F is our thermal, let's see, I'm going to make sure. Thermal fission factor. F will also vary between 0 and 1. And it looks at the number of neutrons absorbed by the fuel divided by the number of neutrons absorbed in everything. So everything would include the fuel, so it'd be the fuels plus moderators. Again, you want F to be as high as possible to keep K infinity high. And again, we're going to go through this when we go through the example in the textbook. Any questions on F? Okay. The final one is nu, which is the reproduction factor. Typically, this one you want to be greater than 1 and as high as possible. In this particular case, N looks at the ratio of thermal fissions creating new neutrons by the fuel to all thermal neutron absorptions in the fuel. Okay? So, that being said, what I'd like for you to do now is, if you have your textbook with you, I want you to turn to page 251, and we're going to be using this typical calculation for the rest of the semester. And what I've done in my book is I put a little binder clip here because I know I am always going to go back and use that in calculations to find K infinity. Okay? So, let's work through the problem that they have done on that page. And again, they have done that a little bit differently than what I'm going to recommend you do. What I'm going to recommend you do is a more precise and correct way to do that. Since we've been going for a little while, what I'd like to do now is take a break until, let's say, 5 minutes, come back at 2 o'clock. I'd like you to glance at page 251. And when we come back, I'm going to solve that the correct way. go through things with you, and then that'll cover up what we're going to do for today, but I do plan to give you a take-home quiz on this. So I will see you in 5 minutes. While we're waiting for everybody to come back, just to mention one other thing when you're submitting your plan of study to me. A couple of you have gotten back to me to say that you're sort of concerned about your grade for Calculus 2 for this semester. Since there is not another math course scheduled for this degree program, you're okay as long as you pass it, and pass it could be as low as a D minus. However, if you do plan to go on to a baccalaureate program in either nuclear engineering, health physics, or even something else, you will need to transfer Calculus 2, and you can only do that with a C or better. So as long as you're going to pass it with at least a D minus, you're good for our program. But just realize that you're not going to be able to transfer it to a baccalaureate program. And should this spring you want to take something like multivariable calculus, calculus 3, whatever, you could not do that unless you have a C or better grade. If you are unsure what you're going to do, the deadline for withdrawal from the fall semester is the second Friday of November, which I believe is the 12th. And you have to make a decision by then. If you do decide to withdraw, and then you're going to take it somewhere else, and that somewhere else could be Straight Align, which is an online institution based in Baltimore. You could do that over the winter break, or you could take it here again next spring, or with Straight Align or elsewhere in the spring. I would encourage you, even though you withdraw from the course, to still attend all the lectures for Calculus 2, so that even though you're not going to get a grade in it, you will have experienced or you will have taken the complete course. So then when you go to take it again, you will have had the full course. Hopefully you can repeat, particularly if you do it with Straight Align. You could easily do this over the winter break and get a good grade in it. Now you still have the option of just withdraw and then never attending anything, but then you will not have experienced the entire course, so that when you do retake it, there's going to be new material in there. So that's just a recommendation for you. The courses that you have to make sure that you pass this semester is Professor Lance's course, because that's a prerequisite for the course in the lab in the spring. You have to pass my 2 courses and 1 lab, because those are prerequisites for the simulator for the spring. If you fall by the wayside in any of those, you will not be able to retake those until next fall. So that would delay retaking the simulator till spring a year from now. So I think there's only one of you that's in academic difficulty right now, and hopefully they can salvage that before the end of the semester. If something happens in the electrical machines class and course that you're taking with on Fridays, you could withdraw from that, either the course or the lab, and there is a replacement course that you could take in the spring. Usually it's either electrical circuits or digital electronics, depending upon what the electrical department is offering. So you could retake those then, and of course you'd have to do a course substitution form. But I would think positive right now. Put in your plan of study when you're filling that out and submit it, that you're going to pass both of them. And then if something bad happens, we can always adjust that later. Okay. Any questions on that? Okay. Let's go back to the problem on page 250. And the 250, okay, problem on 250 says, I want to calculate K infinity for a homogeneous mixture so this automatically implies that the fast fission factor is 1 for 200 moles of graphite. Well, what's graphite? Graphite is carbon per mole of fuel. And for that mole of fuel, it is 5% enriched with U-235, which means the other 95% has to be U-238. So 200 moles of carbon per 1 mole of fuel, but of that mole of fuel, 5% is uranium-235, the balance, 95% is uranium-238. The first thing you need to do when you're working a problem is create mole ratios. And to do that, you select one material to be your common denominator. Okay. You can pick anything, but suggest you pick the lowest mole quantity. So in this case, that would be uranium-233. So if I go back and do that, how many materials do I have? I have 3. I have 200 moles of carbon. I have 0.95 moles of uranium-238. And I have 0.05 moles of uranium-235. I'm going to establish my mole ratios by dividing each of these by the 235. This says 0.05. This says 0.05. This says 0.05. So, if I do this, my ratio for carbon, 235, is 200 divided by 0.05. That value is 4,000. This one is 0.95 divided by 0.05, so that is 19 for the ratio of 238 to 235. And then finally, 0.05 divided by 0.05 is 1, and that's the ratio of 235 to 235. Once you have these, you want to save these. Okay. Now we're going to go and tackle the resonance escape probability. And remember, resonance escape probability is equal to E to the minus N238 divided by squiggle divided by sigma S. All of this times the effective resonance interval. So your textbook says, let's look at the effective resonance interval first. The effective resonance interval is 3.9 times the macroscopic cross-section for scattering divided by number density for 238. All of this raised to the 0.415 power. Now, with this, particularly with the scattering, we have to account for every material there and how that's impacting things. So we could rewrite this as effective is equal to 3.9. And since we have 3 materials, we're going to have to count for 3 of these. So this is going to be N for carbon, sigma C, sigma scatter for carbon, plus N for 238, sigma scatter for 238, plus N 235, sigma S 235. So we're looking at the total macroscopic cross-section for scattering, and we're breaking it down into its 3 component parts because we have 3 materials. And then we're going to divide all this, as it tells us, by N 238. And then we're going to raise this to 0.415, multiply that times this to come up with the I effective. So the first thing we would do is let's divide everything by N 235. Have we changed the value of this expression? No, because if you multiply this out, these 235s will cancel one another out. Before, we did not have the number densities for the materials, but we were able to calculate mole ratios, and we can now substitute those mole ratios. So this guy is 4,000. This guy is 19. This guy is 1. This guy is 19. We could then go back and say, I need to get the scattering value, the cross-section for scattering for carbon. And if you look at the back of the book, because that's where the values are posted, and again, this is on page 577. So if we're looking for carbon, as you go across, you'll see various scattering values. What are we going to use for that value? The scattering value for carbon. What are we going to use and why? If you remember, this is on the fast or epithermal side of K infinity calculation. So we're going to need to use the epithermal value in the back of the text. And the epithermal value is 4.66 barns. If you look at the value for 238 and you go to the back of the book, again, we have to use the epithermal value because it's to the left of that one line, and that value for 238 is 8.3. Then if we go in the back of the book and use that same value for 235, because again, we're thinking epithermal, that value is 10. So I'd like for you, 3.9, I'd like somebody to tell me to do this algebra and tell me what this number is. It's going to go in here, and we're going to raise to the 0.415 value. You've got to learn to do this or else you're sunk. For the rest of the semester, you're going to have to learn to do this. So I'm just looking for the number that's inside the parenthesis when you do this algebra.
Can I interrupt for a question?
Yes.
Yes. So I see when we go to the back of the book, we get our epithermal scatter for carbon as
Yep.
4.66.
Yep.
And then we continue on and we're using thermal values, not
Yes.
epithermal values.
Yes. If you remember back in the last chapter, I mentioned that at times the book is rather chintzy in printing things out. And typically, if they did not print an epithermal value, it was because it was the same as the thermal value and they were just too lazy to present it or print it. So for those cases,
Thank you for clarifying.
if you don't see an epithermal value, that means it's the thermal value. They were just too lazy to print it. Anybody get a number for this? Okay, in this particular case, when you put in barns, the way this is constructed, you do not have to convert that to the 10 to the minus 24th. If you follow in the textbook, it'll show you that in that sample problem. So somebody put a number up, but I missed that. Did you put that back up? We'll just take away the 10 to the minus 24th part of it. Okay, somebody's giving me 979.35. Somebody else is giving me 989.5, I think it was. So I'm gonna see what I get here. Okay, I get this to be 989 point, we'll round this off to 88. Okay? Does somebody get something like that? Hopefully everybody's get something very close to that. Then I'd like you to take this number, raise it to this power, and then multiply that times that, so I have a value for I effective. Let me know what you get for that. I missed the rest of that, the bubble. Could you put that back?
I got 68.27.
Okay. Let's see what I'm going to get here. I got the same thing. Okay. So we know that this value is 68.27. So that means this value is 68.27. So you should be able to manipulate this to come up with that answer. Now let's take and finish this. So the next thing we have to look at here is squiggle. And what is squiggle? Squiggle is if A is greater than or equal to 6, it's equal to 2 divided by A plus 2/3. So we need to look at everything that's here. So we need to look at carbon. We need to look at 238. We need to look at 235. So this is going to be 2 over 12.667. This is going to be 2 over 238.667. This is going to be 2 over 235.667. And very quickly, that guy is equal to 0.158. That guy is equal to 0.0084. This guy is equal to 0.0085. As you can see, this value is much greater than either of these two. And this squiggle is actually an average value for all the materials you have in your reactor. So, in general, whenever you calculate squiggle, the fuels are going to be inconsequential compared to the moderator. So whenever you have a fuel moderator mixture, if you only have one moderator, you can use that value as the average value because it dwarfs the other fuel values. If you have multiple moderators, you have to find an average between those two. In this case, we only have the one. So this value is going to be 0.158. Okay. If we go back and look at this now, resonance escape probability is equal to E to the minus N 238 over squiggle over sigma S over this times I effective. We know our I effective was 68.27. We know our squiggle was 1.158. If we look at this, and we go back and look at what the effective resonance interval was, which was 3.9 times sigma S over N238 raised to this power. If you notice, I had you calculate and keep that number. That number is this. But if I look at this, what's the relationship between this and this? It's the reciprocal. So this is equal to 1 divided by So this whole thing becomes e to the minus 1 times 68.27 divided by 0.185 times 989.88. So, could somebody do that math and let me know what I have for a value for P? .646 is what somebody says. I'm going to check that real quick myself. Yep, that's exactly what I got. So, is this a good value? Remember, our resonance escape probability has to be between 0 and 1. It is between that. Again, we like to keep this as high as we can because we want to keep K infinity high. So this looks like a good number. Anybody get anything different for that value?
Professor, can you move your book because the camera is focusing on the book and distorting the image of the board?
Okay.
Thank you.
Can you see it now?
Yeah.
Okay. Any questions on how we just calculated resonance escape probability? The changes we had from the textbook problem is we've done mole ratios for every fuel and moderator that is there. They took a shortcut and they just said generic uranium. But I want you to learn to do it this way because for your next exam that you're going to take home over Thanksgiving, you're going to be doing multiple fuels, multiple moderators, putting them into a shape that I give you. You're going to have to be able to calculate K infinity. So you're going to have to be able to do mole ratios for everything that's there. So hopefully everybody's gotten that. So we know that epsilon was 1.0. Now we know resonance escape probability is 0.646. Okay. Now we're going to move on and do thermal utilization factor. And this basically looks at all thermal neutrons absorbed in the fuel divided by all thermal neutrons absorbed in everything. Okay. So if we look at this, this says thermal neutrons absorbed in the fuel. We have two fuels, so we're going to have to account for that. So we're going to look at the number density for 235 times the absorption value for 235, and this is thermal, plus N238, sigma A for 238, and again, this is the thermal absorption cross-section. We only have 2 fuels, so that accounts for the numerator. Now we look at the denominator. Now we have thermal neutrons absorbed in everything. So everything includes the fuel. Okay. And again, we do not have number densities, but we have mole ratios. So I can go back and divide all this by and again, I have not changed this equation because if I carry this out, these will cancel one another out. So we know what these values are. This is 1. This was 19. This was 1. This was 19. This was 4,000. Now we need to go in the back of the book and find the absorption values. So again, go to the back of the book and let's look at uranium 235, since that's the first one we have. What is the absorption value thermal for uranium 235? And that's going to be on page 582. Let me know what that value is. No. Absorption. Not scattering. No, it is not 582. Any other guesses? Hopefully you should determine this just looking at it. Anybody else with a guess? Okay. If you look at the back of the book, no, that's for uranium 238. Okay. If you look at absorption for U-235 in the back of the book, it shows you 582, comma, N, comma, F, and 112, N, comma, gamma. So your total absorption is the sum of these two, which is 694 barns. Oops, I put that in the wrong spot. Okay. What this tells you is for every 694 thermal neutrons that are absorbed by our thermal fissioning fuel U-235, 582 of these create a thermal fission. Another 112 of these are absorbed by the fuel, but don't fission. They give off a gamma ray. That's basically a parasitic loss. And there's nothing we can do about that because that is a physical property of the fuel. So, for the absorption, cross-section, thermal for 235, it is the sum of those two. If we go and look at 238, and that's going to be on that same page, hopefully you can see that that value is 2.71. So if we come down here, this value is going to, again, we're going to carry that down. We're going to carry that down. And now for carbon, we again need the absorption cross-section for thermal. And that's going to be back a couple of pages to Page 577, and for carbon, the absorption cross-section for thermal is 0.0034. Okay? Can somebody do this math and let me know what F is for this fuel moderator mixture? Okay, pretty close. I got 0.985. So hopefully you're getting something around that, depending upon how you round off. First thing you might say to yourself, is that a good number? We know that F must be between 0 and 1. We want it to be as high as possible. This is between there. It is high, so that looks like a good number. So if we come over here, we're going to have F 0.985. Any questions on how we did that? Okay. The next thing we're going to do is look at the reproduction factor. And this is basically looking at the number of neutrons created by thermal fissions compared to the number of neutrons absorbed by the fuel. So how many thermal fissioning fuels do we have? We only have one, which is 235. So we're going to have to look at that probability that is causing a fission. And if we went back up here to the absorption, remember, there's a part that's causing fission, and there's another part that's a parasitic loss. And this was gamma. So we need to use that part. And then there is a multiplier, which is nu, which is a physical property of the material. And this for 235 turns out to be 2.43. And there is a table that's up, I believe, in, let me just check. Page 74, which is in chapter 4, lists that factor for all thermal fuels. And what this means is for every thermal neutron that's absorbed, U-235 generates on the average 2.43 fast neutrons. If you go back to that table and it lists them for several fuels, for uranium-233, it's 2.5. For plutonium-239, it leaps up to 2.89. Obviously, the higher this factor is, the more neutrons you're going to create, but again, that's limited by the fuel that you pick. So we've only had one thermal fissioning fuel, we've accounted for that. Now we have to look at total number of neutrons absorbed by the fuel. We have to look at 235 times its absorption. Again, this has to be thermal. Plus the one other fuel, which is N238, times its absorption value for thermal. Okay. Again, these are number densities. We need to convert this to mole ratios, to numbers that we can use. So we're using our common denominator. So this becomes 1, this becomes 1, this becomes 19. From before, we know the thermal absorption for U-38 is 2.71. I've just given you this value, or you can find it in that table. And if we go back to the absorption value for U-235, that split was, let me get the book out of the way again. $582 that create a fission, 111 that are gamma. So the fission part is this part. The total absorption value is the sum of these, which is 694. And this was 2.71. So if you do this algebra, let me know what the reproduction factor is. Anybody got a value for me? Yes. 1.90. So we know that the reproduction factor is 1.90. Hopefully everybody got something close to that. You might have a little difference depending on how you round off things. We've now calculated or found all 4 factors in the 4-factor formula. So we know that K infinity, which is this, is equal to 1.0 times 0.646 times 0.985 times, this is what K infinity is. So let me know what you get for a value there. Hopefully got something around 1.209. Okay. So K infinity for this fuel moderator mixture is 1.209. Notice, we have not said anything about what shape we're putting this in. We haven't said whether this is going to be a sphere, a cylinder, a rectangular solid, infinite slab. No matter what it is, doesn't make any difference. K infinity is independent of the shape that you're putting it in. Okay? Now, I might also ask you, how do you feel about this fuel moderator mixture as moving forward to actually put it together into a core to use in a reactor. Do you think this is good? Bad? You don't know. What do you think? You got a 1 in 3 guess. Anybody want to venture one?
Good.
It's good. Okay? Why is it good? It's good because it is greater than 1.0. Remember, 1.0 is self-sustaining. Let's say our K infinity came out to be 1.0. Is that going to work for us building a reactor? The answer is no. And the reason why is this is an infinite size reactor, so it allows no leakage. In the real world, we know that there's leakage. If there's leakage, this value is going to have to drop below 1.0, so it can never be self-sustaining. So don't even waste your time. That fuel moderator mixture will not function for a reactor core. This one is greater than 1. You'd maybe like to have it a little higher. So it's good. I wouldn't say it's excellent, but it is good. It is viable, and we could go ahead and look forward to using that. Okay. I realize we just covered a lot, and hopefully you followed with me. Any questions on what we did? Yes. Who has their hand up? I can't tell. What's your question? Did somebody have a question? If they raise their hand, I can't tell on my screen here who did it. Okay. Okay. If there's no questions on that, what I'm going to do is I have a quiz on this that I'd like you to do and return before the start of class on Wednesday. So let me go in. And I'm going to send it to you and go over it with you very quickly. Okay, I just sent you the quiz. Let me go over it with you. Okay, everybody has it. I've given you a reactor that has a mixture of 210 moles of beryllium-9. That's another common moderator. Per mole of 8% enriched fuel. And this 8% is 233 for the thermal fissioning fuel. And I've told you that the fast fission factor is 1.02 for epsilon. I want you to calculate K infinity. And then for extra credit for 2 points, I want you to tell me what is the difference between K infinity and K effective. Any questions on the quiz? This will be due at the start of class on Wednesday.
No questions.
No questions, okay. In the little bit of time that we have left today, I'd like to briefly introduce the next topic for nuclear material science. And the next topic is pure bending. So we've had compression, we've had tension, we've had torque, and now we have pure bending. Let's say I have a bar. Let's say this bar looks like my eraser here. And let's say we put a bending moment on it, which means we're going to put a moment. Now, if I use my hands, I'm putting a moment on it like this. So this distorts like this. If the applied bending moment makes the item smile, makes it smile, it is positive. If it makes it frown, we consider it to be a negative moment that's being applied. Okay. If we look at this member before I apply the moment, and we have an original length L sub 0,
Hey, where's your mask?
I'm in here by myself. Go away.
No, can you open this across the hall for me? I don't have a computer.
Middle key. Okay. If we look at this original bar and we start, all these lengths are exactly the same. If we apply the bending moment, these lines distort. And they look like this. I'm just going to do it for the positive. When you do this, what happens to the length of one of these lines on the top of this?
It gets shorter.
It gets shorter. And if it's shorter, we know that's caused by compression. So the top is in compression. The bottom ones get longer. So these are in tension. If you go back and look at all of these lines, there'll be one of these that is exactly the original length that we started with. So everything above this line is in compression, and is going to create a plane stress that is compressive. Everything below that line is going to be in some kind of tension. Okay. This line only exists at one place. We call this line that does not change, we label it in A, and NA stands for the neutral axis. In this particular case, if we look at what's happening on the top part, the plane stress is exactly 0 on the neutral axis because the length is not changed. As we go towards the top, we have compression, and it gets greater the further away that you go, so that the maximum value for compression in this case is on that top line. Conversely, if you go towards the bottom, it's 0, gets bigger, bigger, bigger till you get to the very outside, and this is tension, and the maximum value is going to be the furthest away from that neutral axis. Now, one of the things we're going to do when we have class, probably not on
Justin,
Wednesday.
could you mute yourself, please? Justin, could you mute yourself?
Okay. Thank you. Okay. The thing we're going to do on Monday is we're going to take a shape. And let's say I look at it like this. And in this shape, it looks like this, where this is L in that dimension. When we turn it 90 degrees, it turns out to be a T-bar. This side might be 2 centimeters. This side might be 6 centimeters. This might be 2 centimeters. This might be 10 centimeters. And let's say on this, I show you that I'm applying a positive moment. From just looking at this, we know that the top is going to be in compression, the bottom is going to be in tension, and I would encourage you to label those areas accordingly. The next thing we have to find out is, where does this line occur where the dimension does not change and creates a neutral axis? We're going to find where that neutral axis is. Everything below that is in tension, with the largest value being on the bottom because it's the furthest away from the neutral axis. Everything on the top is going to be in compression, with the maximum value for compression being on the top. How do we find that neutral axis? The neutral axis is the sum of all the areas times their little centroid divided by the sum of all the areas. So what you're effectively doing is finding the centroid of that shape. And that centroid creates your neutral axis. And then you can find out what's in tension, what's in compression, and then we can do some calculations beyond that. So on Wednesday, I'm going to collect your quiz for reactor theory. We're going to go over that very quickly. I'm going to look at calculating a neutral axis for you just to show you how to do it. And I'm going to give you a little quiz that'll be due on Monday in calculating a neutral axis. And then I'm going to give you your exam. And on the exam, you have 2 choices. You can do everything, turn it in by 3:15, and I will give you, I'm still figuring out, 6 to 8 points extra credit for completing it within that time. Otherwise, you have until 4 o'clock on Friday to turn in the exam, and you would do that without the extra credit offered for turning it in early. Okay? Any questions on anything today? So hopefully, before too long, you're going to get to me your waiver form. You're going to turn in your registration by Friday. You're going to do your plan of study form, and you're going to go online and apply for graduation. Okay? I'll be around today till my usual 7 or 8 o'clock if you need to get hold of me for anything. I plan to be in tomorrow afternoon, basically for any registration issues or some other stuff that's going on. Of course, I'll be in on Wednesday. Probably will not be here on Thursday, but I will be here on Friday afternoon. Okay? Any questions on anything? Okay, have a good day, and I'll see you Wednesday at 12:30.